Okay, welcome to the third and final section regarding the variables or factors that affect balance and stability. Here we will be unpacking two of the variables. One is the position of the line of gravity relative to the base of support, and that links very closely to the area of the base of support itself. Okay, so in this object, or in this, I guess, diagram, it's the same object, they just orientated differently. The first one is standing up tall, and in the second picture it's the same object but just lying flat. So there's two things that we're trying to prove, which is to try and say which of these two objects is going to be more stable based on these observed factors over here. And it kind of links very, very closely to what we've already spoken about in terms of the weight of the object, the height of the center of gravity relative to the base of support, so on and so forth. So a lot of the mathematics I won't unpack too much here because it already links to what we've covered in our previous videos. Okay, so how you would unpack this is, say for example I have a pivot point up here. Same thing here, so the pivot point would be the same for both. I apply an upwards force over here, F1, and I would apply that same force on the edge over here, F2, whereby both of these forces are exactly the same. So there's a couple of factors that we need to just kind of unpack. F1 is equal to F2. The masses of both objects are the same. M1 is equal to M2. So we've already proven the fact that mass influences stability. So in this case, both masses are the same. What we're trying to understand now is what effect does the position of the line of gravity relative to the base of support have, as well as the area of the base of support itself. So the first thing that you should notice is that, remember, the base of support is this area of contact, right? Same thing over here. The area of contact you would notice is substantially greater in the second scenario than it is in the first. What we're trying to understand is what happens when I have this center of mass, which would always be acting directly downwards, right? What happens when I apply this upward force? We've already established that that would cause a counterclockwise rotation. In other words, when I apply that force, this object will tend to rotate, right? That tends to affect the distance of this gravitational force relative to the base of support. So as I'm tilting it, in essence what would happen is that the center of mass would still be in the center of the object, but its relative position to the base of support has changed, right? Now it's acting on the opposite end of the pivot point, which would cause and facilitate a further rotation. We've already unpacked the magnitude of that torque force that it tends to create. In essence, what we've proven in previous videos is, would this object return back to its equilibrium position, or would it continue to rotate? And since now the line of gravity relative to the base of support is now outside of this base of support, this thing would continue to topple over. And you can see that that displacement is relatively short, right? There's not much that I would have to displace this because of this base of support being relatively small, right? So a small force causes this rotation, and it doesn't take much for this line of gravity to be outside of the base of support. However, in this scenario, when I apply a force to this particular object and it would cause it to rotate about this pivot point, you would note that it's going to take quite a lot for this line of gravity, right, which is located over here, to eventually fall beyond the limits of this base of support. So even when it is substantially rotated, so if it were rotated to this position over here, let me just quickly redraw it over here. So even if I had to apply a force and cause it to rotate quite a significant amount, the center of mass and the line of gravity would still be within the limits of the base of support, meaning that as soon as I stop applying this force, it would cause a rotation in a clockwise direction until it finds a new equilibrium position. So it would return back to its initial position. So note over here that this angle over here that I displace it is actually quite little for this to become unstable. Notice here, however, that this is a very large angle. We'll just call that phi. This angle over here is significantly larger, and even though it's been displaced such a large angle, the line of gravity is still within the base of support. Okay, so same mass, same dimensions, but its orientation is drastically different. So the position of the line of gravity relative to the base of support has a significant impact, right? Much more stable over here, much less stable over here. Good. So that links closely to the area of the base of support. So the fact is that this has a significantly larger area than this over here, and that significantly impacts where the line of gravity would be relative to some pivot point in order to destabilize it. Okay, so both of these are interlinked quite closely, but that they in essence are looking at two different things. How easy is it to get the line of gravity outside of the base of support, and the other is how big is that base of support to begin with. So hopefully that makes some intuitive sense. Again, the mathematics behind all of this we've proven in previous videos, so this one was purely dedicated towards an understanding of what it takes in order for this to be destabilized. So there's a couple of key things that you can take away from this in terms of athletic performance, in which you can talk about ways of improving stability in order to make yourself as stable as possible, and also how to position yourself in order to make instability a little bit easier, right? So say for example you have two rugby players going in for a tackle position over here. So if this person was going in for the tackle and this person is standing running in this way and he's running in this way, since this person has a lower center of gravity, right, and this person will have a higher center of gravity, this person will be easier to destabilize, right? So when they go in for the tackle situation, who's got the greater sense of stability? A lower center of gravity is better, since that links to this line of gravity relative to the base of support. Second is increasing your base of support. So what this person could do, for example, is to increase how far he brings that one leg forward. That in essence increases his base of support, making him even more stable, right? Think about a scrum situation whereby the person is engaging in a kind of like a tackle situation. Notice that the base of support is much greater, right? So it will take a lot more force from this direction in order to displace or destabilize this person, right? So that kind of links to this specific second scenario over here, right? Increasing the base of support is going to be really important there. I can't necessarily increase the mass, so that's going to be quite difficult to do. So I'd have to play around with different positions, different areas of support and different heights in order to increase and maximize stability. Right, so think about several different types of scenarios whereby it would be easier to displace or more difficult to displace a person, and factor that into your explanations. I hope that has made some sense, and I hope it has provided useful and given you guys some insights into the factors that affect balance and stability.